All right, good morning. Hope you all are doing well. So we've been going through chapter 1, and we left off last time getting in a little bit into logical operators. So at this point, we've talked about all the different conversions. We talked about addition and subtraction. So we're almost done here with chapter 1. But we were looking at logical operators, and we started with the and or operators. And these should be familiar, right? Because you've used them in your code, right? Your programs before in 110 or 165. But we'll review those operators and then look at also two more, which are the not operator and XOR or exclusive OR. And then those were the two truth tables, right? Where a truth table really was just going to represent all of the different combinations that were possible. And the idea was that both and as well as or are binary operators, right? So they work off of two operands. And so here, P and Q, those are just kind of generic variables. And so what we're modeling is the fact that we have two variables and either of them can be true or false. And so the four rows there just really represent the four combinations, right? So P is false, Q is false, or P is false and Q is true, and so forth. And then the third column is the final column where we look at the overall result in terms of when the expression P and Q is true. And so we saw that in particular with the AND operator, the expression only is true if both of the variables individually are true. So the expression P and Q is true only if both P and Q individually are true, and otherwise the expression is going to be false. So that's why we have 3 rows that are false, and then only the 1 row that is going to be true here. And then we looked at the OR operator. So still have 4 rows, right? So we're working off of 2 operands or 2 variables. And the P and the Q columns, again, those are going to be the same because that's just writing out all the combinations of false and truths, or false and true. But for the P or Q expression, right, it's a little bit different because the expression P or Q is going to be true if at least one of P or Q is individually true, or if both of them are true at the same time. So with that one, we had 3 rows that were true, right? And then the only row that was going to be false was the one where both P and Q were both individually false. So that was and an or. Another one that we have is the not operator or negation operator. And so that's a unary operator because that works off just one operand. And so that's going to be a smaller, right? That's going to be a smaller truth table since we only have one variable or one operand to work with. So here we're just going to have two columns, right? P and not P. And so if P is false, then not P is true. Or if P is true, then not P is false, right? So it's a smaller, again, it's a smaller table since we're only working off of one variable instead of two. So that's just your not operator, right? Just flipping false to true or false. Now, the other one that we can look at here is also XOR, which means exclusive OR. And so this is just a variation essentially of the regular OR operator. But we'll say that there's a key difference in terms of how OR works versus XOR. And so P and Q columns are going to be the same. And so the difference here in terms of OR versus XOR comes down to what happens when both of the operands are true. So we know with OR really means one or both, right? If just one is true, then the expression is true. Or if both of them are true, then the expression is also true. With XOR, the X really means exclusive. So we call that exclusive OR. So the only way that that expression is going to be true is if exactly one of them is true and the other is false. So the first line, right, where P is false and Q is false, similar to regular OR, that's going to be it's going to be false also. The second row here where P is false and Q is true, also like regular OR, that's going to be true. And likewise, the third row where it's the other way around and P is true and Q is false, then that's going to be true. But now the difference is this last row, right? Because when they're both true with regular OR, we would say that the whole expression is true, right? In the case of XOR, that's going to be false, right, for that last row here. So P, if P is true and Q is true, then P XOR Q is going to be false. So that's where the, again, that word exclusive comes into play. So only way it can be true then is if one of them is true and the other is false. Whereas with regular OR, it means it's going to be true if one or both of them is true. And so these are four, again, common logical operators that come up. We'll eventually see these come up again in chapter 6 when we get into conditional logic. So chapter 6 is when we start to think about things like making decisions, meaning things that are comparable to if, else, if, else type logic in terms of jumps. So at that point, we'll talk about conditional jump instructions and how you can, comparable to C++, right, model any type of decision structure, whether how simple or complex it is. And we'll see that again in terms of these conditional jump instructions. And we'll also at that time see these operators come up as instructions as well. So meaning that in the assembly environment, we have instructions for each of these four. We have an AND instruction, OR instruction, NOT instruction, and XOR instruction. And in terms of how they work, right, they work based on exactly what we wrote out here in these truth tables. So these sum up all the rules in terms of what's going to happen with the AND operation or OR instruction or XOR instruction or a NOT instruction. So three of them are take two operands, and then the NOT operator, that instruction just takes the one operand. Now, one thing that we'll see first is in chapter 4, we'll look at what's called the NEG or negate instruction, which is different than the NOT instruction. So we talked about 2's complement all throughout chapter 1, first in terms of binary, and then we looked at it in terms of hexadecimal. And just like everything else, right, we saw that it was the same, basically the same idea, except where you have to adjust for the differences in the numbering systems. But we saw that it involved, in a general sense, right, you took the highest symbol for the numbering system, which is 1 for binary or 15 for hexadecimal, and you went through each of your symbols, right, and you did 15 minus that symbol, and so that was step 1. And then step 2 is that you were going to add 1 to the result from step 1. Well, so the NOT operator is doing the first part of that, right? It's doing the part where you, if we're thinking in a binary sense, right, where you're flipping each bit. The NEG or negate instruction does both steps of 2's complement in one instruction. So we have both NOT and NEG, or which is just short for negate. So if you do, the idea is if you do a NOT instruction, then just like this truth table, if you think about your binary number, right, it's going to flip zeros to ones and ones to zeros, but that's it, right? It's not going to add 1 to it. But the NEG instruction, as we'll see eventually, would also do that additional step. So we have different instructions available based on what exactly it is that we, need to do. And so when we think about the, these types of operations, it's helpful to think in terms of a binary sense, because these are really bitwise operators. Although we can think about applying the same idea to hexadecimal, because we know now just how closely related binary and hex really are. But we can look at some examples here now that we've written out all the rules, right, for these 4 different operators. And we'll just look at some examples of how you would apply this to either a binary operand or a hex operand. And the idea is, if we want to think about this in terms of hexadecimal, we've talked previously about converting between all 3 numbering systems, right? Meaning binary to hex or vice versa, and then also converting either binary or hex to decimal or vice versa. So we've looked at all the possible combinations across the 3 different numbering systems. And so, if you're given a problem, like maybe, for example, in a quiz, where you're maybe given some hexadecimal values and it talks about ANDing them or XORing them, well, one approach there would be just to convert them to binary and then run through the process of either XORing or ANDing or ORing or whichever one, with the binary operands, right, and then just take the result and then convert it back to hex. And that's just something that's helpful, because we do think about these operations really in the context of binary, right? So that way we're in line with the truth tables here. Because keeping in mind that when we think about a truth table, one way is representing this in terms of false or true, which is what you might do, for example, in its discrete math type class. But we also know that false, for example, corresponds to 0 and true corresponds to 1. So this directly corresponds to everything that we've talked about in binary. So we can directly follow these truth tables to do any sort of bitwise operation for any of these 4 logical operators. Okay. And so what we'll do here, somewhat similar to some of the other problems, such as addition, we'll just make a little table. And so here we're going to take these 2 binary values. So in this case, 2 8-bit numbers. And we're just going to go through the process of XORing them, meaning that we're just going to follow the rules from this truth table, but for each different bit position, right? Okay, so the first number there was that 1 0, or 1 0 1 0, and then 0, 1, 0, 1. And then the second number we were going to do was that 1, 1, 1, 0, 0, 1, 1, 0. And in this case, we'll look at XOR. And so all we have to do now at this point is just go column by column, similar to how we would think about things like addition, and then just directly follow the rules that we've already established, right, with our truth tables, where again, false would correspond to 0 in this case, and true would correspond to 1. So in particular, and we'll start with the right end, as we did with addition. So the first column then is really just 1 XORed with 0, or true with false. And so that's going to give us 1, because we said before that if you have one that was true and one that was false, then that was going to give you true. And so for the same reason, the second column there is also going to be true, since we have a 1, 1, and 1, 0. Third column, if this were regular OR, the third column would be true, but since this is XOR, or exclusive OR, that's going to be false, right? So 1 XORed with 1 is false. 0 XORed with 0, based on our table, is false. And then so that's false again. 1 XORed with 1 is false. 1 XORed with 0 is true or 1. And then 1 XORed with 1 is false or 0. So then our result is, right, just going to be this 8-bit value. Now, of course, when we think about the differences with this kind of operation compared to arithmetic operations like addition or subtraction, we can also see that one difference is that we don't have things like a carry, right? So in that sense, when we're working off of, for example, two 8-bit numbers and we XOR them, we're going to get just an exact result that's 8 bits, and we don't have to think about things like having a carry out of the MSB, as we did with things like addition or potentially subtraction. So our result there is just that 8-bit value in green, right? That 0, 1, 0, 0, 0, 0, 0, 1, 1. And then again, that's all there is to it. So that's exactly what these instructions are doing when you use them in the in the assembly environment. Or if we want to look at, let's say, let's do maybe AND next. Similar idea, except we'll look at AND instead of XOR this time. We'll take those two binary numbers and go ahead and AND them together. And so similar idea, we'll make another table with those two numbers. And this will be AND in this case. So first number was 1, 1, and then 1, 0, 1, 0. And then the second 8-bit number was going to be 0, 1, 1, 0, 0, 0, 1, 1. And we're just going to go through, and since we're talking about AND, right, we're just going to be directly following the rules that we established here for our truth table, where again, false is 0 and true would be 1. So in particular, we know that the only way AND operation is true, or 1, is if they're both individually true or 1. So the rightmost column is then going to be 0, right? True and false is false. Next column is going to be 1, since true and true is true. False and false is false. False and true is false. And then for the same reason, this one's false. True and true is true. And so that makes that true. And then this one here is false. And so then we get that 8-bit value here in green as our answer. And again, if you're ever given, you know, let's say a hex values, then the easy thing that we can do there is just convert them to binary and then run through them in the usual way, and then just take the final result that we get and then convert that back to a hexadecimal number. So what we can do here, in this case, we're working with 2 hex numbers that both have 3 hex symbols. And we hit on the point before that that correspondence between hex and binary was that 1 hex symbol was going to correspond to 4 binary bits. So these are really just 12-bit binary numbers, right? So ABC is a 12-bit binary number, and then DEF is also a 12-bit binary number. And we saw before, again, we looked at that table that showed the 3-way mapping between all of the 16 symbols in hex and how they map to both binary and as well as decimal. And so we know that A is 10, right? So that's just going to be 1010, right, or 10. So forth. B was 11. C was 12. That would be the first number. And then for the second number, D was your 13. E was 14. And then F is 15, as we know. Down here. So that's what we end up getting. And now we can just directly use those values in our slightly larger table now. Okay, so now we're just going to treat these really as two different 12-bit binary numbers that we're going to go through and go ahead and, in this case, OR. All right, so again, those 4 bits, that's just our A. And then we have the 1, 0, 1, 1, right, that's B, so forth. C. And then we'll do the same thing here for the second number, which was D, E, F, and hex, but we're just, again, treating that also as a, so that's, with these together, that's A and D. And then 1, 1, 1, 0. So that would be together here your B and E. 1, 1, 1, 1. Looking at that together would be C and F for the rightmost 4 bits. And again, in this case, we were talking about doing a regular OR since we already looked at examples of the others. And so now we can just directly follow our table here, right, our truth tables. So it's going to be true as long as one or both individually are true. So now we can just go through this, right? So the rightmost column is going to be true since we have 1 or 0. That's going to be true. If both are true, it's going to be true. In this case, it worked out where they all were going to be true, since we were doing OR. And then at this point, right, so we have a 12-bit result, but if we want to show the result in hex, then we can just take the final result here and then convert it back to hex by looking at these bits in groups of 4s, right? So in particular, take the first 4 bits, right, and then the next 4 bits, and then the next 4 bits here. Which in this case, it works out to where it's just all F's, right? Or 3 F's in hexadecimal. There's another example, and we'll use the same numbers here so we can use most of this again. Well, now we'll look at and again, it's the same numbers, so we're just going to use those same 12-bit binary numbers, but we'll run it through a AND operation. And then we'll take the result and we'll convert it back. So 1 and 0 is false, 1 and 0 is false, 1 and 1 is true, 1 and 1 is true, right? 1 and 0 is false, 1 and 1 is true, 1 and 0 is false, 1 and 1 is true, 1 and 0 is false, and then false, false, true. So this time now we can just look here real quick at an example where it's not all, all the bits are not the same. So in this case, again, it's just important to group them in 4s, right? So take, the first 4 bits, take that as a single hex number, convert it, then take the next 4 bits, convert that to a hex number, and then take the last 4 bits. So in particular, we start here with those, and we know that that's going to be 8, right? So the first 4 bits is going to give us 8, and then the next 4 bits, right, that's your 1, 0, 1, 0, so that's going to give you 10. Okay. And then after the 1, 0, 1, 0, now we have 1, 1, 0, 0, which is going to give us 12 or C. So putting it all together, then our final answer here would just be 8 AC in hex. Okay. And then again, the last one is not, right, that's just working off of one operand. So remember, that's really doing the first part only of 2's complement, right? So the flipping of the bits, but not the adding of 1. So we do have a separate instruction that can do both steps in one instruction. But in terms of the NOT operator, it's only going to flip the bits. So look at a quick example of that. So apply the NOT operator to that binary value. And so we're just going to go through the process of flipping each bit, right? So 0, 1, 1, 0, 1, 0, 0, 1. And that's going to be the final answer. Okay. And so that really sums up how these 4 logical operators work. And we'll see some cases where they're going to be useful, especially in chapter 6. But the way they work really just comes down to exactly what we established in these truth tables here. And so with that, we've really hit on all the major points in chapter 1. And so now we're ready to start getting into the basics of the assembly environment. And so the first thing that we'll look at, and we looked at this a little bit on that very first week when we looked at the things like the move instruction and the add instruction. And as you'll see later today, you're going to be using that add instruction in your 2 programs for your assignment this week. But the first thing we'll need to look at before we get into the Visual Studio environment is the idea of registers, because this is something that's really comes up the whole semester, right? You're very familiar with variables because you've been doing that since day 1, essentially, of 110. And so you have an idea that a variable is just an alias for a location in the memory, and so forth. But registers are also important, right? Because now that we're working at this low of a level, we have to kind of think about the big picture, right? In terms of how all these hardware components are going to come together to make it possible to run a program. And so memory is part of it, but you also have to think about things like the CPU, right? Because as we'll see throughout chapter 2, really, the CPU is what's going to be executing the instructions, right? So all instructions are going to ultimately be ran through the CPU, and registers are storage locations that are directly on the CPU. So when you think about, a modern computer system, you have different types of storage, right, in general. You have your hard drive where you can store things permanently. You have your memory or your DRAM, right, your dynamic RAM, where you can store things temporarily, such as your variables, right, while your program is running. There's a period of time where those variables have to be in memory, in addition to the fact that the program instructions themselves are also somewhere else in memory. And then in addition to that, usually you have things like cache memory, which we'll see that throughout chapter 2. The idea being that that's a faster, smaller, right, but faster type of memory. So if you can find something that you need to access in the cache, then that's going to be quicker than having to access it from DRAM. And then you have registers, right, which are small, really very small in the big picture, right, storage locations that are directly on the CPU itself, right? So it follows that, when it comes to accessing some data that you're going to use, that, accessing it from a register is going to be faster than accessing it from cache, which is faster than accessing it from memory, which is faster than accessing it from the hard drive, right? So you kind of have a hierarchy in terms of, what's a best case kind of versus worst case, right? The hard drive in general is going to be the slowest. And then things like registers, since they're directly on the CPU, that's, your best case scenario, right? That's even better than having to go to things like cache memory. So registers are important, right? They're storage locations that are directly on the CPU. And we have certain registers that can be used in general for program logic, which we call them sometimes the general purpose registers. And so we'll be focused on 32-bit mode, but the book also will usually show examples of 64-bit mode if you're interested in kind of seeing some of the similarities and differences. But so in 32-bit mode, we have 8 general purpose registers. In 64-bit mode, you have 16 or twice as many. But we have 8 general purpose registers that can be used for program logic, right? Meaning things like storing data that is going to ultimately be used in some way, in the current program that we're running. And we call them general purpose because they can be used in general really to store any kind of data value, although we'll see that there's really usually some exception to that, right? There's one register in particular that we usually avoid using directly to store our own
data in our program. But we'll first look at those 8 registers, and then we'll look at 2 other registers that are not general purpose, but are important nonetheless. So we'll look at 10 registers here, and these are all things that you can also see and keep track of in the assembly environment, which will show a little bit how to set everything up in Visual Studio. And you've seen one of the registers already because we really looked at some of the basics idea here on the first week when we talked about the C++ program and how you could take that one line of C++ code and think about doing the same thing but in assembly. And what we came up with was a 3 instruction solution that involved register EAX. And we actually said that you could also do it, you know, a few other ways, but that was going to be the shortest way that you could do it, was that solution that we looked at that involved 3 assembly instructions, right? So that the idea was that that one line of C++ code that was saying something like sum equals num1 plus num2 was going to be equal to the 3 lines of assembly code, right, that we came up with. But one of the things that we used in that solution was a register called EAX, right? So EAX, the E really stands for extended, because relative to 16-bit, you have a larger sized register. So first we'll look at the 32-bit registers, and then we'll see how those registers break down, right, into lower levels. And then we'll talk throughout chapter 2 also about the different modes that you can operate in. But EAX really stands for Extended Accumulator Register. So it's used commonly for things like accumulating results. It's usually kind of the sort of the first go-to register that we use first for those kind of common operations. And it's a 32-bit register, which means it corresponds to type integer, right, in a C++ program, because we've said before that an integer is usually 4 bytes, right, or 32 bits on most systems. So it's a 32-bit register, but we'll see that it also breaks down to lower levels, right, depending upon what level you want to work at, because we've said that there's really 3 levels that we'll be focused on. One is the 8-bit level, or byte. One is the 16-bit level, or word. And then the third is the 32-bit level, or D word, where D just means double, right? So, so the whole idea is that 2 bytes together is a word, and 2 words together is a double word, or 4 bytes together, right, is also a double word. And again, we call them general purpose because we have direct access to them with our instructions. So we talked about things like the move instruction, for example, and it means that we can take any of these 8 registers and directly move a value in it, right? Or use them with other instructions such as the add instruction, which we've also seen a little bit on that first week as well. We'll see that there's one exception really here, but they are all 8 considered general purpose. And then we'll look at a couple other registers that are not general purpose, meaning that we don't have the ability to directly, for example, move something into them, but they are nonetheless registers that come up and we'll be able to see and track in the assembly environment, Visual Studio. Okay, but these are the big 8, so to speak, right? The 8 general purpose registers. the first is EAX, right? Usually when we're doing these kind of things like accumulating results, EAX is usually the one that we would default to and use first. So EAX stands for Extended Accumulator Register. It's just kind of that go-to. So that's why EAX comes up so much, because usually it's the one that we would start using by default first. And so that's what it stands for. The E really for all of these stands for extended, meaning relative to the 16-bit level, which is a lower level that you can work with in terms of registers. So just kind of recognizing the fact that this is a larger size register. And then the A stands for accumulator. So extended accumulator register. The next one is EBX. That one doesn't really have a special name, but it's nonetheless another register that we can use, right? So sometimes, we might have to work with multiple registers at the same time, depending on what exactly we're doing. Or we might choose to do that instead of using a variable. Because again, when you think about things like optimization, certainly accessing a value from a register is, going to be faster than accessing it from memory, including even things like cache memory. So EBX, again, doesn't really have a special name, but it's just another register, another one of these general purpose registers that's available to us. And so, if maybe we're already using EAX for something, and at the same time we need to use another register without corrupting EX's value, then we might use EBX as our next sort of go-to register for common types of calculations. Okay, so that would be your EBX. Again, just another one that we have. ECX does in general have a special purpose, which we'll start to see at the end of chapter 4 when we talk about loops, right? So we're going to see how, things that you're familiar with or very familiar with by now in C++, how you can think about those constructs at a lower level. So things like loops and conditionals. And so ECX really stands for extended loop counter. So the C stands really for the word counter. But ECX is used, as we'll see in chapter 4, it's really used by the loop instruction to keep track of how many times you should keep iterating. So it's used to keep track of where you're at in terms of your loop. Will actually be introduced to eventually some variations, right? So there's the loop instruction, and then we'll eventually see some variations in chapter 6 of the loop instruction. And really all of those loop instructions will use, at least in 32-bit mode, right? We'll use ECX to keep track of where you're at in terms of your iterations. And we'll even eventually look at things like how that's going to work in terms of nested loops, which you can certainly think about at the assembly level as well. But it's used for loops, right? Keeping track of your where you're at in terms of your loop. So in that sense, you know, if we're doing things like a loop, then typically we would not change ECX's value inside the loop, because that just complicates things, because then you have to think about saving and restoring the value. But that's what ECX stands for, right? Just extended loop counter register. We also have EDX. So the first four, right, they all end with an X, and they're just A, B, C, and D. So just kind of an easy way to remember the first four anyways. EAX, EBX, ECX, EDX. And EDX, like EBX, doesn't really have a special name, but it is another one that we have available to us. And so those are the first four, which all end with an X here. And we'll eventually see how these registers break down into lower levels. But those are the first four, but we do have four more. And so the next one we'll look at here is ESP, which stands for Extended Stack Pointer. So it stands for Extended Stack Pointer.